Yay. I'm actually so locked, JT. You don't understand. I pay you saw me. I was like paying attention the whole time, the whole
No,
unit.
you weren't, bro. I saw you on your computer
No.
doing other stuff.
Well, that's only partially though, but like no, before I used to literally not even know what's happening. Now I like even if I'm on my computer for a little bit, like I like take the time to actually try and understand it in class.
I see. That's remarkable.
I know, right? The Albert from today, it's what's
Let's see.
to
That's
8.3 or to 8.4?
8.4. I
Okay.
think.
Let me check Albert then for questions. I'm so tired. What time did you go to sleep last night?
Probably 12.
That's not too bad. Um, approximates the magnetic field at this point. No,
Magnetic
I think
field.
that's well, I mean, it's oh yeah, electric field. Magnitude of the electric field. I read it as magnetic field for some reason. Um, why not? No, I guess I'll just try this one. Just why not? I mean, I think I should figure out. I think I should know how to do it, but I tend to. Do I send it? Where do I send it?
Anywhere, really. Discord is fine.
JT?
Discord's fine. Do you not hear me?
Wait, JT, where do I send the thingy?
Discord? Do you not hear me? Oh my god.
JT?
Hi, Nico. You can hear me, right?
Yo, I hear you
Max's
perfectly
speaker is
fine.
broken, bro.
Yeah, I don't know if his thing's broken. I can hear you though.
Oh, okay.
You hear
Yeah, no,
me?
can you hear him,
We all hear each other.
Nico?
Wait, Max, you talking to me?
Yeah, can you hear JT?
Yeah, can you
Yes.
not?
I can't.
Maybe you have my
Alright,
user
awesome.
volume off. Oh, yeah, he can't.
I should. Can you ask him if he could see my
He
screen that I
said
shared?
he said check your user volume.
Yeah, all right, that's what I'm doing now.
Bro,
I can't see your screen, Max.
Oh, all right,
you
that's
gotta
weird.
you gotta
Something's
click on
going
the
on
screen
then.
share, but it's
Here,
black.
you know what? I'll just leave and then join
Just
back.
send the screenshot.
All right, adios.
Oh my god.
Okay. Yeah, whatever.
I gotta accept you.
Alright. How about first let's go to the AP classroom. Because I just
Yes.
did
Okay,
a question.
now I can hear you,
I don't know
JT.
if it's right.
Okay. One sec. I'm gonna do Nico's question. Which question is it?
Number 2 on the electric fields quiz.
Alright. I'll try and open it.
Because I mean I'm pretty sure I'm right, but I don't know. AI is giving me a different answer, so I
Alright.
don't know if I'm
It was okay, electric fields quiz. Oh yeah. Let's see. Okay. So for this question, alright, so we'll go over the answer. Like our setup is you can do like a force net. Um
Wait, can you share your screen, JT?
oh yeah, I'm not sharing it here, I forgot. My bad.
Yeah.
Okay. Should be able to see that. So
Yeah.
like we'll set up our net field basically. Um our
Oh damn,
initial,
I got it wrong.
yeah, EI, okay, is going to be equal to,
Okay.
since the electric field is like you're imagining there's a theoretical positive charge of 1 coulomb charge, right? That's what it is.
Mhm.
So it's like the same as multiplying by positive 1. So we're imagining at point P there's a positive charge with 1 coulomb being its charge. So that's what so it's going to obviously repel these two forces. So the electric fields will be K Q over d squared, right? Plus k,
Mhm.
or this is a minus actually. So yeah,
But isn't it still a plus because it's magnitude?
but the magnitudes have, it's only magnitude at the end. the magnitude of this entire thing. That doesn't make it a plus
Oh,
though.
okay.
Yeah.
All right.
So then we do minus k q over its 2d squared, so that's gonna be 4d squared.
Mm-hmm.
Okay, so this is gonna give us over a fourth, so that's a whole minus a fourth. It's gonna give us k 3/4 d squared q. Okay.
Yeah, I see what I did wrong, but
Okay.
okay.
Do you want to finish the problem? Should I?
Yeah, sure.
Okay. So now we have since this is a vector, we have to actually look at direction, but you have to realize the signage of this, the sign of each thing doesn't tell you whether the direction. It actually tells you the attraction. It says if it's attracted or repelled. So you have to actually consider the direction. You have to take that into account and implement it
Mm-hmm.
yourself. All right, so in this case, we have a negative charge, so that means it's going to be pulling it in the positive direction. So I'm not going to write negative. I'm going to write positive because it's in the positive direction. It's a vector. These are vectors.
Mm-hmm.
So the negative,
Yeah.
this is from negative q. So on the right, okay? And then we're going
Mhm.
to add the positive q on the left actually pushes it in the same direction. So this is going to be kq as
Does
well.
it say what P is?
So,
Like positive or negative?
no, since it's an electric field, what an electric field is, it's when you divide by the test charge. So the test charge is the charge you place in the electric field, right?
Okay.
So right, electric force is kq1, q2 over r
Oh,
squared.
I see. They're gonna be attracted to
So
each
the
other.
field is
Positive.
kq1 over r squared. So you're pretending that q2, right? They would be the same thing if q2 was 1 coulomb.
Mm-hmm.
So you're pretending they're theoretically 1. So your test charge, an electric field is basically saying what would the electric force be if you placed a 1 coulomb positive charge in that position.
Mm-hmm.
Okay,
Alright.
so since the signs are not different because the sign only tells you attraction or repelling, but since it's a vector here, we actually want the signs to be the same because the positive is going to push it in the same direction as the negative poles. So this is going to be 2kq over d squared. All right, and this is 3/4. This is 2. So if we divide, what is it, EF over EI? So 2 over 3/4.
Yeah.
It's going to give
Is
us 8/3.
8/3, yeah.
Yeah.
Could you do the next question too?
Yeah,
I was
sure.
trying to do it. I have no idea.
Sure. Let's see. All right, sure. So what's important to note is that this is not starting at the origin, right? So our net electric field, okay, is going to be equal to k. It's a field, so we have the test charge is at x3 essentially. So it's going to be k, which is k is I'll write it as 1 over 4 pi epsilon naught. Okay.
Epsilon naught.
Yep.
Mhm.
Times q1 is the first charge we'll set up. Okay.
Mm-hmm.
But the distance over radius squared. But the distance between x1 and x3 is not just x1. It's x3 minus x1 because x1 is not 0 per se.
Mm-hmm.
So the radius is x3 minus x1. Okay. Squared, because
Yeah.
that's the formula. q1 over r squared. So this is r squared. Plus
Mm-hmm.
another k, because there's another field vector being added on. Epsilon naught times, it's now q2 is positive. Now note, since these are both on the same side, if q2 was a negative q2, then it would actually, you would subtract it.
Okay.
But it's not, so. Alright, now over the distance between x2 and x3 is x3 minus x2 squared. And now we just factor this out. So 1 over 4 pi epsilon naught q1 for x3 minus x1 squared plus q2 over x3 minus x2 squared. That makes sense?
Mm-hmm.
So like you have to think, even though the signs of these plugged into the electric field equations are positive, that means they'll push this x3 test charge away if it was there. But if we moved q2 to the right side of x3, it would repel it in the opposite direction, meaning you'd have to actually negate the value of the electric field.
Alright.
Because electric field's a vector, and the signage of the electric fields, like from this formula, let me show you. The reason there's an absolute value bar there is because this only tells us the magnitude. The sign doesn't tell us, this equation can't tell us the direction. We have to figure out the direction intuitively based on where it's placed and if it repels or attracts. That's why there's absolute value bars.
Okay, now why do you like separate the equation into two different things? Is it because it's two different
Sure.
distances,
Well, because
two
these are
different
like,
radii?
these are electric fields caused by two different charges. So we
Okay,
could like,
yeah,
we could remove Q2 and then we would just have this part, but we can add them
yeah.
together because that's just the way the property works. So
Okay.
yeah.
Alright.
Max, was there one you wanted to do?
Yeah. Okay. Let me on the Albert, I think it was actually yeah, sure. Just do 8 on the second Albert. So 8, 3, and
I
8,
low-key
4.
got a 6 and a 9 on that. That's fine. You said on the second
Okay.
Albert, number 8?
Yeah. Number 8.
Okay.
I think
So,
after that I'm gonna do wait, is that the same question? Wait, am I an idiot?
is this the
Uh
question?
yeah, 8 out of 15.
There's not 15 questions.
He said the Albert, not the
Wait.
AP
Oh, this is
classroom.
not. Oh, my bad. I probably got
Yeah,
less
the
than
Albert,
that.
not the AP classroom.
I probably got even less than that. One
Wait,
sec.
is the AP classroom also due tonight?
Yeah,
Uh, did is it one of them or is it two of them?
Bro,
2.
what the hell? Why
Both
is
of
he
them are
doing
due?
that?
Yeah. But that's what I gathered. Okay.
Dude,
So
that's
let's.
so annoying.
Okay. Yeah. Well, he gave a long time to work on it, unfortunately. So, all right. So, what is the value of a field at a distance to the right of the charge? This is just, you just use the field formula.
Yep.
E equals 1 over 4 pi epsilon naught times times 8q over the distance is 2r, so it's 2r squared. So that's 8q over 16 pi epsilon naught.
Wait, JT, hold on. No,
What?
no, no. The questions are scrambled. I don't know
Just
why, but
describe the question.
huh?
What? Each question has a
It's
name.
point
What's
P is located 2 meters
no? What's
to
the
the
name of
left
the
of it.
question? What's the name of the question?
Point P is located to
No.
which of the following?
Look at what I'm showing you.
Yeah. Okay.
See how these have names.
Oh, yeah. Okay. Uh, electric field due to a line of charge.
Okay. Cool. Okay. So this is literally, so you have to sum up all the electric fields. So we have the electric field. It's only going to be in the x direction, obviously. It's going to
Yeah.
be equal to k times the integral. It's times q over r squared.
Mhm.
Okay. So the rod has a total charge of so we can literally just, it's just this dq, okay?
Mhm. Yeah.
And we find that I think you can just literally do.
Oh, and it doesn't matter what the rod's
So
charge is, or is
the rod's length is equal to um we'll look at that in a second.
would R just be like like the integral bounds would it just be 2 to
2 to
5?
5, yeah.
Yeah. And
Well,
then
dq,
and DQ is charge differential, right?
yeah, yeah,
And
lambda
charge is just constant. So yeah, it's just a constant times
lambda.
VR.
Oh,
Okay, yeah.
but lambda is equal to that charge 2 times 10 to negative 6 coulombs
Yeah, okay.
over 3 meters. So that's how you would solve
Oh,
it.
you divided by meters.
Yes.
That's important for me to know. Okay, that's good.
Yeah, that's how you solve this.
Okay.
R squared is what?
R squared is the
Here.
distance between the point and each little like atom in this rod.
So what is it, 3?
It goes from 2 to 5 because the
Oh,
closest distance is 2, the furthest is 2 plus the
yeah.
length of the rod.
Okay. Alright.
Yeah. So that's 10. I don't know that we actually want to do this, but 9 times 10 to the 9 times 2 times 10 to the negative 6 over 3. Negative. So 2 to 5. I'll just. I doubt we actually need to do this, but so it's 3 times 10 to the 3 times 2. It's okay, half minus a fifth. Yeah. So what is that? 18,000? Yep, got it. Okay.
Yeah.
No calculator needed.
Nice.
Okay.
All right, Nick. Is it okay if can I mute for a couple minutes so I can go downstairs and grab something? Like, can I not
Yeah,
get
that's
kicked
fine.
from the thing?
What's
All right.
wrong, Rayhan? I like how it shows this. This is DQ as some little portion of charge.
That's gonna be so confusing. Is it
Yes.
like Gauss's?
We're not doing Gauss's law for this quiz.
JT, can you like go over
that.
some concepts? Because like I'm
Like-
like I low-key forgot a lot of stuff.
Yeah,
Yeah.
I'm lost also.
Let's see. Sure.
Like any big concepts, you don't have to go crazy in depth or anything. I just want to like know some basics.
Coulomb's law should be known. It's the force. So you have to remember, like I said, important thing. The equation for like the force and the electric field, it only gives you the magnitude. You have to actually figure out the direction because these are all vectors, so they have magnitude and direction. The negative or
Yeah.
positive sign tells you if it's attracted or repelled. If it's negative, if it's a negative sign, it's going to be attracted. If it's positive, it's repelled. So then you have to go use the context of where the objects are relative to each other to determine the signage of everything. So, okay.
Mm-hmm.
Permittivity is just like how easy it is for electricity to flow through a space, I think. Yeah. So that's that constant, the epsilon naught. It might give it to you. Conductors allow charge to flow through. Insulators don't. Conservation of charge. Charge is conserved, obviously. Electrons aren't going to spawn in. Methods of
Mhm.
charging. Conduction is just like when you touch objects together.
Yeah, I know that. Wait, what does that say? If a charge is transferred
To
to
an
an
insulator.
insulator,
I don't know why it would be to
excess
an insulator.
charge
One sec, Spencer.
will remain at the location of
Allow
charging.
for charge to transfer the free movement of charge to an insulator. Interesting.
Hmm.
Okay.
Is that just a thing you have to know?
I don't know why it couldn't be through
The conductor.
yeah.
Wait, what's the difference again between the two?
A conductor allows electric charge to flow through it. Also, charge tends
Oh.
to group on the surface, like it tends to go outwards towards the surface. That's
Uh-huh.
important to know. There was like
Okay.
there was an AP classroom question that asked about electric field inside of a charged metal sphere, and there
The answer is like towards the sphere,
it
right?
would be 0 towards the center because no fields towards the center because there's no charge on the inside. Really, I guess it cancels out.
I think there are two questions like that.
What can we skip again? I forgot. What did he say?
We're not
8.2?
doing like the newest stuff we haven't done. Induction.
No. Didn't he say 8.2 because he couldn't find any questions on it?
Maybe, probably.
Yeah, didn't he say
I
that?
don't
Or
know,
what's
it's-
8.2?
Right. What is 8.2?
I have no clue. It'll probably be clear. Induction is like when you group all the charge to one side of an object by using another charged object.
Oh, okay. That makes sense.
It's like, remember when we have those two spheres that are touching and then you bring like a negatively charged rod towards one side, then you separate the spheres?
Yeah. And then what's an induced charge?
That's like that.
Is that just that?
So like
that?
so like the example I give is, let's say we have two negative spheres, right? And we have
Mhm.
and we have a negative rod, okay?
Oh, that's what you just said.
So let's say we have a negative rod, right? This negative rod is gonna push away all the electrons here. So all the electrons are gonna go into this
Ah.
ball. These balls are touching each other.
Oh.
Got you.
Then the
Oh,
balls
Gotcha.
separate, okay? So now this ball stole all the electrons from that
Oh.
ball. And now this
Oh.
ball is very positive, this one's very negative,
Oh,
but this
okay,
never
one's
touched
hairy.
them.
Okay.
Yep.
JT, did you go over the derivation for the semicircle?
Oh, we can.
That's not gonna be on the
Why not?
quiz. There's no shot.
That's
It's a multiple choice.
well, it could ask for it as an answer.
Can we go in
Oh,
order still
okay.
until we get
Okay.
there?
Yeah, so grounding is like, let's say you have a negative object, you touch it to the ground, the earth is assumed to kind of be neutral, but it's so big that it'll take all the excess charges and it'll make everything neutral.
Oh, okay.
Okay. Other
Mm,
important concepts.
oh, this
Uh,
is 8.2. This is what he said it wasn't
oh,
gonna be on the
okay.
quiz.
Well, my bad. Electroscopes, is that
I
on it?
just
Wait, how
remembered.
do you know 8.2 is not
Oh,
gonna
it
be
does
on
say
it?
8.2
He
here.
said he couldn't find any questions on 8.2,
Oh,
so it's
Okay.
not gonna be on the quiz.
Electric
yeah,
field
like this.
is just force divided by charge. It's imagining that it's imagining a force with a positive test charge of charge 1 coulomb. So it's saying like if you place the charge here and its charge was 1 coulomb, how would the force like move as a vector?
Ah,
So it always points away from positive because positive repels
okay.
positive. Electric
Always
field
it points
equation.
away from positive and towards negative.
Yeah.
Okay.
Electric field equation, that's just in the reference table. Let's
Well,
see.
it's like the wait. Can you go back to that slide for a second? Sorry.
It's
What is it
E is
saying
F
on the
over
bottom?
Q. This is just saying it's similar to the gravity equation. And he's saying
Oh,
this
okay,
because
okay,
later on we'll see a relationship between them when we do Gauss's law.
okay.
So
Wait, Nico, is that what Ben was talking about today with related rates?
Huh?
Do you remember what I'm talking about?
Nope.
okay, so
You don't pay attention.
electric fields can be added together. That's kind of what we did in those questions earlier. Just like forces are added together. Electric field due to a dipole.
What is this?
No clue.
Right, yeah.
I think
That's
I think
why.
it's just saying you can draw like a, so let's say we draw like we have a negative charge and a positive charge, right? We know that the electric field's gonna flow away, like this kind of. It's gonna go away from the positive,
Mm-hmm.
and it's gonna go towards the negative.
Yeah.
So you can just sketch it. I think that's all it's referring to.
Okay.
Other things, let's see. Integral definition of electric field. That's just K. This is as a vector, but I don't think
No.
Is that on the reference table?
the vector form. Yo, whose microphone is that?
Rayhan.
That's not me, bro.
Yo, did I? Okay, 1 sec. What did I do? I just clicked something. Oh, I hate when that happens. Yeah, I accidentally sent someone an invite. Okay. Let's see. Alright. So this is what this is saying is since electric field's a vector, you can basically use, instead of, you know how we have displacement as a vector, right? Instead of
Mm-hmm.
doing like the r squared, we can actually multiply it by r hat, which is the direction. R hat means a unit vector, so it means like magnitude is 1. So since the magnitude's 1, it has no effect on the magnitude if you multiply it. But it's like a direction. So it's saying,
What's the point in doing that,
so
though?
it's, well, it's saying the direction of the electric field is the direction of the displacement. That's what it's saying.
What does that say on the bottom? The R over.
Okay, so this is the equivalent form I wrote. R hat is equal to R over the magnitude of R. So this is R squared. This is the magnitude of R squared. So these
Mm-hmm.
two are equivalent, the forms. So that
Yeah.
dq, I moved it out, but it's saying, so R over magnitude of R, that those double like lines means magnitude. So that's equal to R hat. And then I kept the R squared from before, so it's R cubed. You don't really,
Okay.
I don't think he would test on this. I don't.
Yeah.
Yeah, I was gonna say when do you use that, but
You could
Uh,
theoretically, and we actually kind of do use it, but that's like when we do the rod, and so we wanted to do a rod. Was that
Nah, this
Yeah.
semi. Oh,
semicircle? Okay. Let's see.
it's like one of the. It's like an 8.4, I think.
Oh my god, my scroll bar is not working. Okay, let me just. Semicircle. Disregard everything I have here. Okay, so we're gonna. I'll set this up.
He posted his notes on
Yeah,
Google
yeah, yeah.
Classroom.
I'll redo it, I guess.
bro, his notes. They're just so weird. Nah.
They're not always the best. Okay, so we're gonna I'm gonna construct the axis. I'll remake it how he made it. Okay? Let me. So we
Dude,
have
what is he even writing, bro?
so we have the x-axis.
Jack wants to be able to speak.
Yeah, well, he talks too much, so he'll wait.
Jack, what are you doing?
Okay.
It's not ridiculous.
Okay. Y-axis.
The main thing I don't understand is like in the final answer when he leaves it in terms of L where like he pulls out lambda and
I'll
then it's
show you.
Q.
There's some interesting things going on there. So our angle is going to be theta, radius r. All right. So what we're going to do is we have to recognize there's symmetry here, and this is going to make our question a lot easier. So what I mean by this is that for each point on the field, on this, so this is charged, right? There's going to be a charge density of plus lambda, okay? Plus lambda. And there's going to be radius r, right? This is just our facts. Radius r, okay. So for each point on the field that pulls the field this way, there's an opposite point that pulls it to the opposite direction, and they all have the same charge. Meaning there's going to be no x direction of this electric field, only y direction. So we're finding the electric field at point O, alright? And we're going to find the y direction only, which is really important, alright? So our field formula, we're only doing Ey because Ex is equal to 0. So this is going to be K, so dq 1 over r squared, okay? But since we're only looking at the y component here is going to be, it's the cosine. So
Yeah.
we're going to do cosine of theta dq. Now we've got to do some important things here. We know that what? Yeah, okay. So we know that lambda is going to be the total charge over, so it's saying the total charge over this, let me redraw this, the part that we're actually looking at. So this is the part we're trying to, this is the semicircle. I can't draw. So that's like, you're imagining it's some sort of object. The density of the object would be the mass of the object over the volume, right? So in this case, we're imagining it's kind of one-dimensional almost, or two-dimensional. So the charge density would be the charge of the object, the total charge of it over its length here, which we're actually going to change length later, but this is what we have. And it's also going to be equal to dq over dr. So it's important to recognize this dr is saying like you take a little portion of the length. So like something like some tiny fraction of the length would be dr.
Yeah.
All right. So let's do this. So we have lambda dr equals dq. Who is that, bro? Is that Rayhan? Like the echo?
No, not me.
Okay. We're gonna substitute this in. I'm gonna pull it all out. Ey equals k lambda, because these are constants. And now we have to figure out the parameters here. Or cos theta.
Yeah, it's from negative pi over 2 to pi over 2.
Not yet, actually. This is still in terms of dr, so it's not quite. So now we also have the, that wouldn't be correct yet. It would be different.
Yeah.
So we also know this equation, like, you know, S equals theta r. Remember, big R refers to the radius of this object. Little r refers to a tiny piece of length along it. So in this case, it's actually, the relationship we're using is, instead of writing S, we're gonna write little r. So this is like circumference almost. Okay, and when we integrate,
Like, could you use another variable because you use the
no, well
little
that's what's commonly used. We can sure, we'll
Then-
change it. We'll do, instead of dr,
You have like d little r for the little sections on the length too.
that's correct. That's what it's supposed to be. The little r is the sections of length.
Yeah. So
And-
why do you little r is the circumference?
Well, it is. dr is a little section of the circumference. A little section of the length is a little piece of the circumference of the
Yeah.
semicircle.
Yeah.
So dr equals r d theta. So look, a little bit of a change in angle here times the radius is going to be equal to that little portion. Okay? And what's important to note here, it's actually ambiguous because everything's ambiguous in physics. This r is not referring to the little circumference. It's actually referring to the distance between the circumference and the point, which I can't draw a straight line. So it's actually referring to, this here would be actually big R squared. So we have to actually change that, and it will be ambiguous, but because it's not math class, it's physics class, you won't lose points if you replace it eventually, even if they say ambiguous at first. Okay, so now we have to substitute this dr in. We're substituting that in for r d theta. Okay, so let's do this, and I'm going to pull out the 1 over r squared. So we have ey is k lambda times 1 over r squared. And now we have r d theta. Yo. Okay.
Yo, Rayhan, mute yourself, bro. Okay, there we go. Good, my mic's been muted this whole time. I knew it wasn't me.
Yeah, so cos theta r d theta. Now we can actually put the angle in. This angle here is going to be pi over 2. This is negative pi over 2. Since it's from the top. If it came from here, we would go 0 to pi. But like it doesn't actually matter in this case. So negative pi over 2. Pi over 2. What we notice, we have an r here and a 1 over r squared here. So I'm going to take out that exponent. And I'm going to take out this r. Okay, so let's integrate it, k lambda, and now this is over r still, and then we're going to evaluate this. Yeah, antiderivative of cosine is sine of theta from pi over 2 to negative pi over 2. Okay, now k.
Why don't you do it in terms of theta at the start?
Because
so you don't
can't. They're not equivalent. Because you need to get this r somehow, and if you don't, you got to do the conversion. Like, you could jump the steps, you wouldn't lose points, but there's a chance you're going to make a mistake. Like, you need
Can't you do, like, q over... Oh, no, I guess. Q over L, but then, like, your length is 2 pi radians?
Yeah, well, that's what we're going to do after. But that's
So
but that's all a constant. The length is a constant, so we can do that at the end.
Okay.
So sine of pi over 2 is 1. And then we subtract the second value, sine of negative pi over 2 is negative 1. So that evaluates to 2. Okay, so that's 2. Now, lambda is equal to, as we said before, so we have 2k for r times lambda, but lambda is q over L. And L is the length of this semicircle here, the blue semicircle. And the length of the semicircle is going to be the circumference of it, which it's the circumference of a circle is 2 pi r. So the circumference of a semicircle is going to be pi r. So L is pi r. So
that's what
yeah, so sometimes you can just leave it in terms of L if it says to do that, but sometimes you want to actually change it in terms of R. So we're going to make this pi r. And this is really important because now look, we get 2k q over pi r squared. And what's significant about this is that it matches the reference table formula. This is k q over r squared. K, and here we have k q over r squared times some other constant here. And this constant is dependent on what the object setup is. So, yeah.
Oh, I see. When I was doing one of the AP classroom questions, the formula was 2kq over pi r squared for the semicircle.
Yeah. So this is the y component. If we solve the x component, we would do the same exact thing, and I'll show you why we don't do the x component. 1 over r like before. But instead of having the cos up here, we would have had a sine to begin with. So sine theta.
Doesn't work.
D theta. So if we do this from pi over 2, or negative, right? If we integrate that, we get a cosine. And so let's see what happens. Well, it's a negative cosine, but I'll pull out the negative. If we evaluate the cosine of pi over 2 is 0. Cosine of negative pi over 2 is 0. So we get a 0 here. That would 0 it out. So the x component is going to be 0. So that's why we only solve for the y component.
Yeah.
Now, if it's a semicircle, is it always going to be that 2 over pi kqr squared?
Well, if the r changes or the q changes, then you have to account for that. So.
Well, yeah, but usually when it's a semicircle in the front, it's always that 2 over pi.
Also, you know what else you could see it as? Remember k is 1 over 4 pi epsilon naught. So we might
Yeah.
have to substitute that in. So we'll get what is that? Q over 2 pi squared epsilon naught r squared. That's something
If-
else we might see. I think that was probably even in the Alberts or something.
Yeah, if he's giving us 20 questions, I don't know if we're gonna have enough time to derive all of it.
He didn't say 20. He said nothing more than 18.
He told our class 20, but I guess he was capping.
He told us nothing more than 18 when I'm pretty sure.
Oh.
JT, do you mind going through the electric fields quiz numbers 4,
Probably got them wrong, but yeah.
5, 4 through 9?
that
Can we
AP
just do the
Classroom?
rest of it? Yeah, it's AP Classroom because these are all.
Okay, 4 through 9. You said
Yeah.
got 4 wrong. Oh man. See, this one
Is it C? Oh, I knew it. Yes.
the
Okay.
electric field is always perpendicular to the surface
But why is it
of a conductor in an
Why?
electrostatic situation.
I'm so confused on why is it why are the lines curved? Are they just
Okay, so in this
like
one,
that?
the lines are not perpendicular to that inner surface.
So,
So like the lines always have to be perpendicular to all the surfaces. So you have to
But
find the one that
why aren't
satisfies
they?
it. Why is that the case?
Yeah.
Well, according to this, electric field is always perpendicular to the surface of a conductor in an electrostatic situation when it's not moving. Here, okay, that's just something you have to know. Like when we did the thin rods today, the assumption was that the electric fields were perpendicular to the surface. So,
Alright, so it's usually gonna be A for them, but this is the one outlier
well,
case.
no, it's usually going to be C because they're usually perpendicular to the surface.
But that's not perpendicular. Am I stupid or?
Well, look at where it's not perpendicular. Well, the arrow curves such that like the arrow here is perpendicular to the inner part of this ring. It's perpendicular.
Oh, because it's a circle, it has to curve to be perpendicular. Okay.
Yeah, and then it's perpendicular to the part it comes out of. It only has to be perpendicular when it exits and enters, I guess. Which is weird,
Okay.
but I guess we just have to know that. Which he did not explain.
Now for 5,
Oh,
is
fine.
it just one with charge?
Sure. So,
Is it just the KQ over R squared plus KQ?
so
over
one
R
charge, okay, is separated by distance d at the midpoint. So we can set this up. So it's 3/2. Okay, so 2 charges. So for setup 1, right? So the electric field E is a vector, remember? So it's going to be in between them. So the positive one's going to push it away and the negative one's going to attract it, right? Does that make sense? Since it's an electric
Yeah.
field, it goes away from positive towards negative. So they're both going to
Wait,
have
is that always any electric field?
electric fields always go away from positive and towards negative because it's imagining that you have a test charge of 1 coulomb, positive 1 coulomb. So it's like a proton.
Oh, so it's just always gonna approach negative.
Yes, yeah.
Okay.
Okay, so we have positive, so K, Q over, since it's going to be the midpoint and the distance between them is D, it's going to be D over 2 squared. And then even though the signs are different, the absolute values of them are the same. Plus K, Q negative here over D over 2 squared. So that's going to give us, what is that? A fourth plus a fourth, so K, Q over, so I'm tripping. So this is going to be a 4 up here. I think it's going to be 8 d squared. Yeah. So when you add those, that's what you get. Now, okay, what is the magnitude if one of them is doubled? Okay, so let's see. So S2, situation 2, E is equal to, now the positive one it said was doubled, so K, Q times 2 over D over 2 squared plus negative K, Q over D over 2 squared. So this is now going to be equal to, that's becomes 4 on top times 2 is 8 KQ over D squared plus, what is that, 4, assuming I did this right, so that's 12, versus this is 8, so 12 over 8, right, what is that, 4/3, is that right? No, 3/2, what am I saying, 3/2. So this is
Yeah.
the second one when you multiply this charge by 2. And then when you take the ratio, it's going to be 3/2.
All right, and that's the positive charge.
They're both pulling in the same direction. Whereas if the positive and negative charges were on opposite direction, like the negative charge was moved to the left of the positive charge or something, like if they were on the same side of the test charge, then they would actually, you'd subtract them instead of adding. That's why it's absolute value
Wait,
bars here.
aren't they going different directions?
Well, the so
Because
the test charge here, let me show you the setup. So the test charge is, so we have a plus Q here, okay? We have a minus Q here, okay? And they're separated by
Yeah.
a distance D, okay? But
Okay.
you're placing a test charge here, T, a test charge.
Yeah.
So the positive is going to push it away. Electric field lines always go away from positive and towards negative. So they're both pulling. One's pushing it,
okay.
the other's pulling it, but they're pushing it and pulling in the same direction.
Yeah.
Whereas
All right.
the only way we could change this was if we moved the negative Q over here. Then the negative Q would be pulling it, but it would be a lot weaker than that positive Q because it's farther away.
That makes sense.
Yeah. Next one you said?
I'm just going through the whole thing.
Yeah, sure.
'cause-
Okay, halfway between. So look, a positive and a negative again, and we're putting a test charge in this in between. So they're both gonna pull and push in the same direction. So I'm just gonna, so 3Q K over the distance is gonna be D over 2.
But
So
it's just gonna push with a much greater magnitude, right?
yeah.
Because 3Q.
Yeah.
Okay.
Over D over 2. See how I have the negative, but I have absolute value bars? Because we have to assign the direction ourselves. The formula can't give us the direction. But actually, do you know what formula can give us the direction? This is really interesting. So, look, remember we had a formula before that Rayhan was like, what is this? So see how we have like this R hat? This one doesn't have
Yeah.
absolute value bars because this R hat actually has direction.
Because it's
So-
X direction. right?
Yeah, because this is displacement, so it's saying displacement times the charge. So this one you actually don't need absolute value bars. This would work. It
So
does
don't
this.
you use that
You can use
always
this.
like in the X direction?
You actually
Always.
you always use this, yeah, but we don't write it like this because it confuses people. Because
Okay,
you
yeah.
basically add, when you multiply by R hat, that's just saying if it's going to the right, add a if it's add a positive, if it's going to the left, negate it usually. So that's what that R
Alright.
hat means. It's just direction. So,
Yeah.
but we don't really worry about that too much. Okay, so we do this, we get, this is gonna be 3 times 4, I think. I don't really want to do that. 12 KQ over D squared plus 4 KQ over D squared. So that's 16. And then 16 times KQ over D squared. But K is 1 over 4 pi epsilon naught. So that's going to give us 4Q over pi epsilon naught D squared, which is answer D.
I feel like a bunch of these you can just skip a bunch of steps, right? And then just figure it out. Once you're done with that first step, and if you know 1 over 4 pi epsilon naught, you can just straight up skip.
I
that.
mean, you can't really guess these. The answers are too similar.
Yeah, I mean, well, wait.
I mean, I don't think you can really skip steps. Like you could, yeah, I would. So you want to know how I actually solve this? Because I know that it's that electric field, right? I know it's proportional to charge, right? And it's inversely proportional to radius squared. So that's all I write. I just write it like that. So I just do.
Yeah.
How I set it up is I do 3 over 1/2 squared. 1/2 squared plus 1 over 1/2 squared. Like I don't write anything else because it just saves me time. Then I get 4 plus 12, 16.
Oh.
And then I divide by 4 pi epsilon naught, or figure it out.
Okay.
This is just, since I pulled out the constants here,
Mm-hmm.
This is like if we wrote, so electric field is actually equal to, we could just write this. Look, electric field equals k q over d squared times all that. So like I can just evaluate these, then tack this on afterwards. Saves me some time. But like I don't think you can really skip steps because you don't want to lose anything essential.
No. Okay. Yeah. Okay. So for the original one, it's 16 on the top, and then you just put the 1 over 4 pi epsilon naught, and then that
Yep.
simplifies to 4.
Yeah.
And now, wait, where'd you get the scroll? Can you scroll up a little bit?
Yeah.
Yeah.
This is a k12q, 4kq. Because it's d
Where'd
over
you get
2
the
squared. So d over 2 squared, you pull the over 2 squared to the top. Because like dividing a denominator is the same as multiplying. Like 1 over 1
Oh,
half.
because it's d over 2 squared, and then you just multiply
So
by
it's like
4.
1 over 1 half
Okay.
squared.
Yeah.
1 over.
All right.
Yeah, 1
Okay.
fourth.
I have to brush up on the algebra skills.
Yeah, that's fine. Next one you wanted to do?
Yeah.
So how do we do this one? Okay. So it's hanging from a string. So that means that the net force in the y direction is 0. We had a question similar to this on a midterm. So F net y is 0, okay?
0
newtons. So it's going to be equal to the force of gravity, or rather the force of like electric force, Fe, minus Fg. Okay, so Fe is going to equal Fg. And Fg is going to be mg, is going to be equal to k. And then check this out. In the reference table, we have electric field, right, is equal to Q times Fe. So Fe is equal to Q times electric field, okay? That's from the reference table.
So you can just set those two
this is
forces
all we
equal
need.
to each other.
So now it's saying
JT, will you still be here in like 10 minutes? Because
Yeah.
I have to run,
Yeah.
and can I be back in 10
that's
minutes and
fine,
ask some
that's fine,
questions?
that's fine.
Alright, cool.
Okay, so it's saying on the moon gravity, or G, is going to be 1/6 of Earth. So it's going to say, how can we change it to make this equation still hold true? So we're going to mg over 6 is equal to, okay, so check this out. What we can do is, we could rewrite this as, I would rewrite it as 1 equals GE over, I'm sorry, Q, that's a Q. QE over mg, okay? So now we have 1/6. 1/6 is equal to that. QE over mg. Like, you don't have to do it like this. But now you got to find what changes will make this equal to 1/6 times this. This is equal to 1. So if we multiply mass by 3, this is mg, right? If we multiply mass by 3, we have a 3m down there. And then if we decrease charge by a factor of 2, so that's saying multiply charge by 1/2. So we get, that's equal to 1/2 q, right? E over 3mg. So that's going to become 1/6 times QE over mg. So that works. That satisfies it. So when it says decrease by a factor of 2, that means divide by 2.
Okay. So basically, for these questions, what you want to do is just go look at all the answer choices and see which one works.
Yeah, that's how you have to do it. Fortunately, it's the top one.
Okay, that makes sense. And can you always just set mg equal to that QE?
Well, because it said it's hanging, we know that F net y is 0. You have to look at the context
so you can
of the
set
question.
the forces equal to each other.
Yeah,
Okay.
yeah.
Alright.
Okay. 2 positive point charges, 1 Q fixed in place. Okay. Electric field. So we have a charge Q here, okay? Q, positive Q, and plus 2Q, okay? What we want to notice is that these are both distance D. They both repel, right? They both repel a positive charge. So if we put some test charge here, they're both going to push away. So that tells us that there's some point in which Q over R squared is equal to 2Q over, check this out, D minus R squared. And why is it D minus R? Because at this point here, right, this is going to be R is 0. So the distance from here to here is going to be D, right? So when we plug R at 0, the distance is D. But when the distance of this charge is all the way at D, D minus D is 0, so the distance would be 0. So D minus R squared. So this is the equality. Charges cancel out. So we get D minus R squared equals 2R squared, okay? Now, It's not asking us to solve it, but it's saying which would hold true. Since these forces repel each other, we know this holds true. Let's say it said negative Q here. That would mean that this is also going to pull in this direction. So there's no point in which they cancel each other out, right?
Mm-hmm.
But let's say now we move the test charge over here because it's negative. If the test charge was over here, now this force is going to push it, but that Q is going to pull it back. So it would, but because the Q has a smaller multiplier, there's never going to be a point in which this actually works. It would have to say like 20Q and 2Q, but it doesn't. So there's not ever going to be a point in which this is strong enough to cancel it out. But if we put it over here, let's say this is when it's negative. The question's not asking. If we put the test charge here, Q is weaker than 2Q, but now Q is a lot closer to T. So there's a point at which it would cancel it out. Okay, so let's suppose it's positive, like the question says. This is, let's say if it asks us to solve for the distance. This is how we would do it. D squared minus 2dr minus plus r squared equals 2r squared. And I hope they would never ask us to do this, but you never know, so we're going to do it. 0 equals r squared plus 2dr minus d squared. Now, this is kind of like you could let r equals x. We have actually a quadratic formula here. We have like 0 equals x squared plus 2dx minus d squared. So negative b is, I'll write this out. A equals 1, b equals 2d, c equals negative d squared. Okay, so negative 2d plus or minus the square root of 2d squared is 4d squared minus 4ac, so plus 4a, so plus 4d squared. Okay. I think this is correct. Let me see. Yeah, okay. Over 2 times a over 2. All right. So we're going to pull those 4's out. So negative 2d plus or minus 2d rad 2 over 2. So x, this is like the position, equals negative d plus or minus d rad 2. Okay, so if we, so rad 2 is roughly 1.4. Okay, so what this tells us is that like if we did 1.4d minus d, that would give us like 0.4d. So let's look at that intuitively, because you should be able to intuitively grasp it. So it's saying because they're positive and they both push, there's a point around, so like let's say 0.4 is roughly, what is this? How many dots is this? 1, 2, 3, 4, 5, 6, 7, 8. So 0.4 is like 2/5 of 8. I don't know. Let's say it's around here. So if the test charge was around here, okay, this point here, the magnitudes of these electric fields would be equal. That's how we solved it algebraically. The magnitudes of those fields would be equal, and they would cancel out. So it would have 0 force there, so it wouldn't move necessarily. So that's how we solved it algebraically. But it also tells us, okay, but one thing you have to understand, this gave us a plus minus. The alternative it could give us is x is equal to negative d minus d rad 2. But this doesn't work because this is going to give us some really negative number that would be far over here. But the issue with this is that the direction of the force caused by this charge is going to be different over here. So we would have to use a different equation, so it wouldn't work. It would have to be, the value that it gives us would have to stay within this range, otherwise it would be invalid. So we got a valid value there, like roughly 0.4d. Okay, so should we do the next one? Did you want to do 9 or no?
Can you go back to the 8 for a second?
Yeah.
Just for a second. So, but like since just for this question, how is it gonna be 0 if if one is 2q and one is q? How do they ever cancel each other out?
Yeah, sure. So, well, like I showed the setup here, let's look at this setup, okay?
Yeah.
So the electric field, E, okay? You agree that, so this is Q, this is 2Q, so obviously this is going to be stronger, right?
Yeah.
Overall. But distance but the strength of an electric field is inversely proportional to distance, okay? To distance squared, rather. So if we get it close enough to this charge, the the lesser distance that it has, that the fact that it's closer to this
Oh,
charge than that charge will mean that the electric field of this charge will be a lot stronger here. So at some
okay.
point it'll cancel out.
All right. I
Yeah.
got it.
So that was like our setup here. We had electric field equals K times Q over R squared minus, I did the minus because see how we draw the direction of the electric field, they're opposing directions. So that's why we have a minus there. It has nothing to do with the charge. Minus 2Q
Okay.
over D minus R squared. Okay. So that's how we do this. Then we solve this equation for R. And that'll give us, that gave us 1.4 times D, roughly. Or 0.4 times D, which is like over here. So like roughly
Right.
around here they would cancel out.
Okay.
Check this out. Actually, I want to show you this. I'll show you why this works. Look at this.
All right.
I made it. This may make it more confusing. We'll see what happens. Okay? So I made this Desmos thing, right? And now check this out. Look at this. Let's see. We're going to place a charge, okay? We're going to do some distance D. Let's say D is, we're going to make it 1 meter. Oh no, we'll make it, 2 meters. So check this out. Would that be best? Let's try around here. So these arrows, actually, as these are both positive charges, okay? But we can basically find a point such that they'll cancel out. I don't know if we can do this here. Let's see. Yeah, I don't think I'm gonna be able to do it. But let me look at the arrow between these. I want to show you this. The length of this arrow is virtually 0. You see that? How these arrows are all really long. Well, they're slightly longer, but like this
Yeah.
this arrow is roughly 0, as opposed to, see, this arrow here is, let me make it thicker. How do I make it thicker? See how this arrow is like long and these are long,
Mm-hmm.
but this point in between them is roughly 0 length.
Yeah.
That's because they roughly cancel out in the x direction. Even though this
Okay.
this blue charge has twice the Q. Its Q is 2, but this one's 1. But they still roughly, they cancel each other out almost at some distance. So, yeah. If that makes any sense.
It does.
Cool. All right. Is there another one you wanted to do?
Let me see if is 9 gonna be on the test? Because it's like one of those conducting questions.
Was it this one?
Yeah.
That's a good question. I would say recognize that I had to look this up, but okay, the electric field is 0 within any conductor that is in electrostatic equilibrium. Outside a spherical conductor, the field has the same inverse square dependence. So it should make sense. This answer should be very intuitive. You're just inverse square law. So it's like there's an asymptote at like 0. It never reaches
Mhm.
0, but as you get infinitely far away, it approaches 0. The electric field strength. But inside of it, there's 0 fields, which is really interesting. I guess they all cancel out. I don't know. It's just because like all of the electricity goes to the outside. I think you just have to kind of memorize that.
All right.
Yeah.
I don't even know. Is this? You think the other one, the fields of charge distributions, is that one harder?
I got a lot more wrong, but that doesn't mean anything. I probably put less effort.
Because
Yeah,
I
you wanna look at
haven't
it?
started that one. Yeah, sure. I haven't
Well,
started it.
that's
So.
much more convenient for you.
Yeah,
Since I-
it's much more
let's see
convenient,
what I
so I
got.
can
Let's
review
actually
and
see
do
what I
it.
got wrong. That'll give
Okay.
us a better gauge. Okay, I'll do this one. This one's a good one. If he gives us a lot of questions like this on the test, we'll probably be in trouble.
Oh, but I noticed that like these questions, like if you look at all the notes too, you can just automatically recognize the answer to this question.
Sure, yeah.
It's like, because like if you
The
see
3
that
halves.
the 3 halves and also whatever the distance is, whether it be r or d, from like the center of the thing to whatever point it is out there, it's always on the top next to the q.
Mm-hmm.
Wait, what was I gonna say? So, but the radius for this thing is always constant. The charge is always constant. So can't you just
That's why it
integrate?
cancels out in the x and z component, but the
Yeah.
horizontal component there, you gotta actually find it. So that's why we set this up as like, so if we look at the electric fields of a given point on the, we'll draw it this way. We're gonna take one point out of the ring, so this is the side view from the ring.
Yeah.
We're gonna give it some arbitrary angle theta. We don't need to know theta yet. So the distance is we're gonna do the derivation because I think it's good to know. This is point P. So this is somewhere along the ring. Okay. So
Yeah.
if we know that the y component's gonna cancel out, so we're only gonna look at the x component, and the x component is gonna be, that's cosine, right? Adjacent over hypotenuse. Okay. This hypotenuse is r squared plus d squared. Okay. So if we do the setup, Ex is equal to k, and then let's set up lambda first, equals dq over d. It's not gonna, I'm not gonna do dr, d length, okay,
1 second, Matthew FaceTime me. Sorry.
equals q over l. Okay, so let's set this up. It's k times dq is lambda dl over r squared. Lambda, I'm gonna pull the lambda out, dl. But since I want only the horizontal component, that's times the cosine of theta, okay? Cosine of theta, dl. But now we know the formula for cosine of theta, actually, because cosine is equal to adjacent over hypotenuse, which here the adjacent is d, the hypotenuse is r squared plus d squared. So cosine is actually equal to, check this out, d over the square root of r squared plus d squared. Okay. So we're going to substitute that into here. And this little r, this is actually going to be r squared. That's the radius, the distance. No, it's not. I'm tripping. That little r we'll have to solve for. So that little r is the distance from any point. Any point along the ring has a distance. They all have the same distance from point P. And their distance is going to be this hypotenuse, right? So imagine this is like the top of the ring. So it would go around like this. Let me do that better. The ring would go around like that or something. So any given point would have the distance r squared plus square root of r squared plus d squared, right? From point P, that should make sense, I hope. So that's what we're plugging into here. That's square root of r squared plus d squared. So let's do this. Let's plug this all in. Ex equals lambda k, and then we're gonna go. You good?
No.
Probably. I figured not. Okay. So in that down there, we're gonna plug in 1 over the square root of r squared plus d squared, all this squared because it says to square it, times, okay, times this cosine is d over square root of r squared plus d squared. So this is, the square root is the same as to the 1/2 power, and this is to the 1 power. So 1 times 1/2 power is going to be 3/2 d length, I guess. Okay, we're gonna have to, this integral is not correct right now. It can't be evaluated, I don't think. So, okay, so we get d over r squared plus d squared 3/2. Okay, and length is gonna go dl, but I guess it would just, oh, you know what it is? You know what the trick is? I think this is the trick. So you don't need the lambda here, okay? You just have the k. We don't need any of this, actually. So we have the k, and we keep it as dq. That's the trick here. So we replace the cosine, right? We replace the cosine with, this is dr. Okay. We replaced, I'm sorry, dq. The cosine was replaced with d over square root of r squared plus d squared. We keep the dq here. We keep the dq here. But the thing is, the charge along the thing goes from 0 to q. So since the charge is the same at every position, and we don't actually need to work with charge density, we could just do dq here. So this is basically a trick. It's a trick. We're summing up all the charges along the thing, but they all have a charge of q, or like somewhere between 0 to q, because the total charge is q, right? Okay, so when we do this, since this is all a constant, we can pull it out. K d over r squared plus d squared 3/2. I know it's kind of confusing, but 0 to q dq. So that just evaluates the q, big Q. That's q, and k is 1 over 4 pi epsilon naught. So that's how we get that bottom answer. Kind of interesting. We can use the dq here because these are all all we can represent like a little change in charge here. A little bit of charge is just like dq. We don't, it's kind of weird, but you don't need to do it in terms of anything else. Like you could, but it's unnecessary. I don't know if more justification is needed. What do you think?
I think we're good.
Okay.
Wait, JT.
Yeah.
If the ring has a total charge of q, like, don't you need to do the thingy where you divide it like q by
Use the
the
density.
what?
Use the charge density. You don't have to do that here.
No, I'm saying you have to divide q by like the number of meters or something.
No,
To get
that's charge density. Charge over
okay.
length, charge density. You don't have to do that for this question because, well, the charge is
You're just
uniform.
using the total charge, and you're just yeah.
The reason is the charge is uniform throughout, but the we basically summed up. We found an equation that represents the distance essentially. So like, so every single point has this same distance in the x component. It has the same
Yeah,
x
isn't the
component of
distance to d squared, d squared plus r squared?
This is the x component of the distance. This is the x component
Yeah.
of the distance, not the y. So they all have the same x component. So if we multiply each x component by like a tiny fraction of charge, and then we know that the sum of all the tiny fractions of charges has to be q, so it's just the same as multiplying by q. So we can do that for this question. It works.
Okay.
Did you get anything else wrong on this one?
That's a great question. I probably
Didn't he say it's gonna be way easier than these like AP classrooms?
Well, let's hope so. We'll practice this.
Did he?
Whoa. Oh, this is stupid. I'll do this. I can't believe I got this wrong. Okay, so I don't really want to do this. They all have the same charge density. So we're gonna redo that one, but now in terms of charge density, like Max asks, because this will actually be beneficial. They only have a y component here, so EY equals K, lambda, and then it's gonna be 1 over square root of radius squared plus d squared, d over here to the, I'll do it to the 3/2. 3/2. Okay, dq. All right, and so actually, do we even need to? Now this is just our equation. So we can just use this equation. So we have kq lambda, and lambda is going to be, actually no, we don't need the lambda here. Kq times d over r squared plus d squared to the 3/2. So they all have the same distance. The d is 10. 10r, so that's going to be like 10r plus 100. But we actually, I guess we do want a q. Lambda is going to be, they all have the same charge density. Lambda equals, it's going to be q over I guess it's a matter. Lambda times sorry, lambda times whatever the circumference is going to be equal to the charge. So q like the object is lambda times 2 pi r. So we can plug that in there. Lambda 2 pi r. Okay. So times 2. So we have an r squared up here. No, that's an r times d. Okay. So for each one, we have they're proportionate to r over r squared plus 100 to 3/2. So I guess if we plug in all these values, let me make a new Desmos thing.
JT, why is it d? Why are you multiplying d by everything?
What? The d was already there. That's just the equation we derived in the last question.
I wasn't there for the
Well, you can
derivation.
go rewatch it. So let's do 1 over 1 squared plus 100 to 3/2. Let's see if this works. And then the next radius is 2 over 2 squared plus 100 to the 3/2. Yes, so, and then the next radius is 100 over 100 squared plus 100 to 3/2. Okay, so these are clearly, well, I want to say that, let's see what the correct answer is. So 2 is greater than r is greater than 100 is what we got. This is 100, it's very little. 2 is the biggest, then 1, then 100. You can use that same relationship before, knowing that the charge density is constant. So charge density times the circumference or the area is equal to the charge. So you replace q. Like in the previous question, we just had q, but we can replace the q with q equals lambda circumference. Lambda times length, lambda L. So that's kind of how you do that. And then you use the equation from before to do all this stuff.
Wow.
Yeah, not pleasant.
You probably wouldn't put that on there. Not that evil.
Nah, I don't think you would. Could be on the AP, but I don't know. They're not going to put a lot of questions that take too much time.
We're gonna be committed to college. Who cares?
Yeah, that's true. Although the credit would be nice.
It would be. Like, I'll get the mech credit and dip.
Let's see. What else I got wrong? We did this.
What the?
Oh, this is. Oh yeah, this is because the x
Oh.
component. This is because the x components cancel out, and it's only the y component. I think. Yeah, so you have to do that 3/2 thing times d again. Just
Yeah,
like
doing all
the
that.
ring. It's like just like the ring, the x components cancel out, so you only need the y component, so you have to do the 3/2 things again, and then you have to multiply by d.
I see.
This one you multiply by 2d, and this one's by d. Oh, so okay, this is actually really interesting. I like this. So you know how the y component is going to be the cosine of the angle actually. So look, it does use the r hat like in the formula, but it says r hat is the cosine of theta. So then it finds the cosine of theta using your right triangle. So that's where you get the cosine from. That's the r hat. It's the direction. I guess
Okay.
that's interesting. I don't know.
see. Oh, can we do a question like 1 where it talks about like symmetry and stuff?
This.
Yeah.
So like you just think for each point you figure out on top, right? It's gonna have a y
Mhm.
component and an x component. So let's for semicircle, that's a semicircle, supposedly. For each, let's say we choose a point here, right? It's gonna pull
Yeah.
up this much, and it's gonna be a bit to the left and a bit upwards. So there's that y component. But there's gonna be an opposite point on the bottom with the same y component, but the x components will also be in the same direction, so they won't cancel out. So every single y component will have an opposite y component that cancels it out, but
Mhm.
the x components will double.
They're all in the same direction.
Yeah, so the electric field has a non-zero magnitude. The magnitude of the field's in this direction. Every point on the arc produces a field that cancels the vertical but not the horizontal field component.
Does it say C? Is C here like the point, like the
C is like a
electric
test
field
charge.
point? Yeah, the test charge.
Yeah.
So
It's
the
positive.
arc is always like going away from it, like
Yeah, but
repelling it.
even if C was negative, it would still cancel out. It would just be the opposite direction.
Yeah. Okay. All right. Makes sense. Why is nobody else here?
I don't know. I guess I don't care. It's second semester.
I mean, I really shouldn't care this much, but like,
But you don't want to fail, because if you fail too many, you'll get rescinded
yeah.
offers.
Gotten in so far.
What happened?
Nico, where have you gotten in so far?
I got into Stevens the other day,
Oh, nice.
and RPI I got into yesterday.
Nice. Did they give you a bunch of money?
I got like 30,000 a year from Stevens, and then like 38,000 from RPI.
Damn, I got the same amount from Stevens.
Yeah, I know. Yo, Stevens gives no money. Pissing me off. I want to go there so bad, but I'm gonna call up the financial aid office and be like, yo, can you guys please give me more money? But I think you call them after the FAFSA has been filed, like after they give you your FAFSA back, and then you can ask for more money.
The
So,
normal tuition.
if I'm dorming, 81,000 a year.
Yeah, that's a lot.
Yeah,
Nothing is
exactly.
cheap. I like the
JT.
campus.
Mm-hmm.
It's small, but it's nice. A really nice view.
It's a very small and beautiful view, but I like that. Like, you don't want to be at it. I hate those huge schools. Like, you don't learn anything.
Maryland is one of my top choices.
I mean, but like, it's a good school nonetheless. I mean, I hate the
It's
schools
a
that are
biking
like
school.
huge.
Maryland's a biking campus.
Yeah. Well, actually, no. To be honest, RPI is like has one
I
of the biggest
visited.
campuses I've seen.
I don't even remember how big it is, but I know it was big. Alright, are we done with studying? Because I gotta study for golf.
Yes, if you want to be done, JT, we're done.
Cool.